It's my great honor. Let me introduce our next speaker today, Leandro Vendramin from the University Brussels, who will tell us about Nichols algebras, our solvable groups.
Thank you. So I will share my screen if I find my presentation. I don't know, where is my presentation? Okay, I found it. Just 1 second here. Very good. So thank you again for the possibility to give this talk. My plan is to discuss Nichols algebras over groups, the classification of Nichols algebras over group, and in particular, I would like to mention a recent result done in collaboration with Heckenberger and Andruskiewicz on the classification of these objects in the case of solvable groups. So first of all, I will start with a definition of a braided vector space. This is just a vector space over some field K, and together with a bijective linear map from V tensor V into V tensor V, satisfying the braid equation, which is this equation that I wrote there. It is called the braid equation because of the picture. You have this pictorial representation of the equation. This is also known as the Yang-Baxter equation or the quantum Yang-Baxter equation, depending on the papers. And yeah, this is the starting point. You start with a vector space with a braiding, which is this map C. And then, well, from this, you are going to construct these objects, which are called Nichols algebras. But before doing that, I would like to mention two examples, or two families of examples. The first one is some sort of the flip map and some variations on the flip map. So you take a vector space with a finite basis like this, and then, well, flipping just elements will produce a braiding. And you can twist somehow the flip using these non-zero scalars there. And it doesn't matter which scalars you use, but you will always get a braiding. This is kind of easy to check. And these braided vector spaces are known as braided vector spaces of diagonal type. This is the first family of examples, very, very important. And the second one is some sort of generalization of that. Essentially, well, the fact is that conjugation will also give you a braiding, or will give braidings. Just to give you like the correct setting, let's say that G is a group, and then take X as some union of conjugacy classes, some subset of G stable under conjugation, and then you take as V the vector space with basis in this conjugation stable subset, and then conjugation, like this formula that I put there, will give you a braiding. And again, you can twist somehow a bit with some non-zero scalar to produce other braidings. This is different from the case that I discussed before, because it's not that any collection of non-zero scalars will give you a braiding. So there are some equations that need to be satisfied by the Qs, but in any case, once you fix a union of conjugacy classes of a group, then you have a lot of braidings that you can consider. All these braidings are known as braidings or braided vector spaces of group type. Okay? Now, what can you do with them? Well, every time you have a braided vector space, you produce a representation of the braid group. Just recall that the braid group is the group with these n-1 generators, and the defining relations are, well, you have a braid relation if for two consecutive generators, and then if the generators are kind of separated from each other, then they commute. And you will produce a representation of the braid group just replacing a generator sigma I by the braiding, applying the braiding in position I and I plus 1, which is what I wrote there. I mean, this is well known, but I will give you I will show you a very concrete example, so maybe it's easier to see. So let's say that n is 4. So the braiding is this picture that I wrote there. Is just a way of flipping like two elements in a way. And then C12 is flipping the first two strands of this configuration of 4 strands that we have when n is equal to 4. And C2 is flipping the strands 2 and 3. right? And these are this is the representation of the braid group somehow that you produce with a braided vector space, right? The C is precisely the way in which you flip two strands. Okay. Now, every time, as I said at the beginning, every time you have a braided vector space, you produce an algebra that is called the Nichols algebra of the braided vector space. It will be more than an algebra. It has more structure, but I don't want to discuss this extra piece of information that you have. I will just give you the definition of this object as an algebra, right? So what is this? Well, it's some crazy quotient of the tensor algebra. It will be a graded algebra by non-negative integers. In degree 0, you will have the base field. In degree 1, you will have the braided vector space V. And then you will have, V tensor V with some relations in degree 2, V tensor V with some relations in degree 3, and so on. And these relations are computed as the kernel of some linear map, which is known as the quantum symmetrizer. So here I give a very explicit description of these quantum symmetrizers. It's a recursive formula. So the first quantum symmetrizer you see there is this sigma 2 or S2 is identity plus C, which is a linear map from V tensor V into V tensor V. Then the third quantum symmetrizer is this sum that I wrote there. So like you see here, I have 6 terms. So in fact, what you do to get this is to run over all the elements of the symmetric group S3 and then decompose every element as a product of elementary transpositions. And then instead of using the elementary transposition, say Ti, you replace this by the map Ci using this representation of the braid group I defined before. And this is how you define all the quantum symmetrizers. And well, in general, you have this recursive formula, right? So, well, this is the definition of a Nichols algebra. It's kind of clear that these are complicated objects to work with, right? Because even though this is a very explicit, say, description, and you can just use a computer to try to, to compute some defining relations, some kernels of symmetrizers, at some point you cannot just continue computing, right? Because this really grows very, very fast. Okay, but it doesn't matter. You can still do a lot of things. Let me give you some examples of Nichols algebras. So these are not crazy objects, right? They appear somehow in nature. So the basic 2 examples that you should maybe keep in mind are the symmetric algebra over any vector space V, which is realized as the Nichols algebra of the braided vector space V with the flip. Okay, just switching V tensor W into W tensor V. And if you put a minus on the braiding, on the flip, then you get the exterior algebra, okay? So the first one is infinite dimensional, the second one is finite dimensional. And somehow these 2 examples also tell you why, it's kind of easy to see that these objects are rather important, right? In fact, these Nichols algebras were found independently by different people, right? Several people rediscovered Nichols algebras. Like in physics, for example, they are known as Fock spaces. Of course, in physics, since they don't care about finite dimensionality or something like this, they need some extra completion or something. But algebraically, this is just the object you are dealing with. And in pure math, well, they first appeared in a work of Nichols in the 70s, studying certain type of Hopf algebras. Also in the work of Voronovich, he was doing some differential calculus on some quantum Lie groups, say. In the work of Lustig, studying quantum groups. In the work of Majid, doing non-commutative physics. In the work of Andruskiewicz and Schneider, doing Hopf algebras. And all these people somehow found an alternative definition of a Nichols algebra and used Nichols algebras for what they were doing, right? So the problem I want to discuss is, well, the classification of finite dimensional Hopf algebra, Nichols algebra. And why I want to do this? Well, because this has kind of an immediate, not immediate, but a very important application in the theory of quantum groups or in the theory of more general Hopf algebras. But of course, I mean, to make this reasonable, not because it's easier, but just because of the applications I have in mind. I don't care about, or I will not consider every possible braiding. I will treat Nichols algebras as invariant of groups. So the braidings I will consider are those braidings of group type that I defined at the very beginning. Okay. So, but there is a better way of presenting these braidings of group type. There is a more algebraic framework, and is using the language of Jeter-Drinfeld modules over groups. So you fix a group G, and then a Jeter-Drinfeld module over say G or KG. It will be a graded G module. So you have a grading by G, and also you have a G action, and then you have a compatibility, which is this formula using conjugation that I wrote there. Okay, and Jeter-Drinfeld modules form a very nice category. So it's a tensor category, but also comes with a braid. So you can make a tensor product of two Jeter-Drinfeld module to get a new Jeter-Drinfeld module. And also for every Jeter-Drinfeld module, you have a canonical braiding, which is that formula that you see there. Okay. So this is the kind of the braided vector spaces I want to consider, right? So what about the classification of Nichols algebras over braided vector spaces of group type? Of course, you can split the problem into two pieces. So either you consider abelian groups, and then you will have to deal with these braidings of diagonal type, the first example of a braiding I gave you, or you can consider non-abelian groups. And then you have these, braidings of group type over non-abelian groups. In the case of braidings of diagonal type, the classification problem is solved in characteristic 0, and there are some partial results in positive characteristics. In the case of non-abelian groups, well, there are, again, two subcases to consider. Either you think that your braided vector space admits a decomposition, whatever it means, or it doesn't. If it doesn't admit a decomposition, the problem is still open. But there are some results that I would like to mention. And in the case of decomposable objects, this is completely solved, even for all characteristics, not only in characteristic 0. Okay, and I would quickly try to mention some results around this picture that I have here. Okay, so remember, this was the definition of a braided vector space of a diagonal type. This is a Jeter-Drinfeld module, essentially over an abelian group, right? This is the formula of the braid. So the Nichols algebras over this family of braided vector spaces have a lot of applications and very interesting problems. So as I said, the classification of the finite dimensional ones, say over complex numbers, was achieved by Heckenberger about 20 years ago. A very precise or explicit presentation by generators and relations was found by Anchiono. There are a lot of applications, very strong applications to the theory of Hopf algebras, or more precisely to the theory of pointed Hopf algebras. Remarkably, here is the classification of Andruszkiewicz-Schneider, which I like to think that this is some sort of axiomatic way of presenting small quantum groups, or if you want, finite dimensional quantum groups. And there are also applications to physics, to conformal field theories, in the work of Semikhatov and also Simon Lettner. But this is not what I want to discuss here. I don't want to talk about finite dimensional Nichols algebras over diagonal type braided vector spaces, but on the other side, right? So over non-diagonal Nichols algebras. So why we care about this? Well, they again are quite important in the theory of Hopf algebras. Some Hopf algebras that are somehow a bit different from quantum groups, and also they appear in other places, remarkably in Schubert calculus, in some sort of combinatorial approach to Schubert calculus. I will try to quickly mention something about this. So as I said, right, you split the problem here into two pieces, into two sub-problems. You either deal with indecomposable braided vector spaces, whatever it means, or decomposable, right? But I need to give you a definition because it's not just decomposable or indecomposable as a G module. It's something slightly different that involves the braiding that you have. So for decomposable, as I mentioned, it is solved. How does it look like? Well, let's start first with the definition of decomposable when you have two summands. So it all starts with this remark by Matthias Grania that says that if your braiding is symmetric, so if the square of the braiding is the identity, then the Nichols algebra of B plus W is nothing but just the tensor product of the Nichols algebra of B and the Nichols algebra of W. Say as graded vector space, which for us is enough, right? Because if I just want to consider infinite dimensional Nichols algebras, then, you know, if I know the simple pieces, then I don't have to care, right? So when you have a summand of two, say, simples, and the square of the braiding is symmetric, the square of the braiding is the identity, then I'm not really in a decomposable, proper decomposable case, right? So to be in a proper decomposable case, I want to assume that the square of the braiding is not the identity. So this will be my assumption for the decomposable case, at least with two summands, right? And then I need another technical definition, which is the support of a yet-to-dream-for module, which is the collection or the set of elements such that the G homogeneous component of B, you remember that it was a G-graded G module, so the G homogeneous component is non-zero, right? And yeah, the support of a yet-to-dream-for module will be a union of conjugacy classes, right? Will be precisely this guy that I was considered at the very beginning. Now, with Heckenberger about 10 years ago, maybe a bit more, no, 10 years ago, say, we proved this. So we gave a full classification of the groups that can produce a finite dimensional Nichols algebra over a braided vector space with two indecomposable summands, say, right? So namely, this is like this. So you start with a non-abelian group, then you have two simple or absolutely reducible yet-to-dream-for modules. So absolutely reducible means that it is irreducible even after extending the base field, right? This just doesn't matter. So you have like these modules B and W, and you assume that G is generated by the support of P plus W, which means that, you know, this is your G is precisely what you need to realize your modules. Then the square of the braiding is not the identity, just to be sure that you are in the decomposable case. And the Nichols algebra of B plus W is finite dimensional. And then I can describe, up to central extension, I can describe very precisely what is G. G will be a quotient of a central extension of SL23, the group of 2 by 2 matrices of determinant 1 and coefficients in the field of 3 elements, or a central extension, a quotient of a central extension of a dihedral group, which can have order 4, 6, or 8. So it's a very precise description of the groups involved in this case. And with this, you can solve somehow all the problem, right? So for example, you can get a very precise description of the structure of B and W, and you can also get the dimension of the Nichols algebra of P plus W. So how does it look? Well, like, just to simplify a bit, let me tell you what happens in the case of the complex numbers. So you have a non-abelian group again, and then you have two irreducible yet-to-dream-for modules over the complex group algebra of G. Again, you consider the same assumptions. So G is generated by the support of your module, the square of the braiding is not the identity, and the Nichols algebra is finite dimensional. And then, well, I can describe which Nichols algebras can appear. I cannot put all the information in this slide, but I can give you, say, for example, the dimension of P plus W, which can be 4, 5, or 6, or the dimension of the Nichols algebra, which are these numbers that you see there. Okay, and very good. So this is what you see for complex numbers. But of course, the theorem holds for arbitrary characteristics. It's not that only works for characteristic 0. It's just that you have more examples, right? Like, this is the full list. So again, the dimension of B plus W can be 4, 5, or 6, but there are more possible Nichols algebras that you will find. There are some, for example, that you will find only in characteristic 2 or only in characteristic 3. Okay. Very good. This is the solution of the composable case in the case of having 2 summands. If you have more than 2 summands, well, you need again the definition of the composability. And in this case, it's kind of same thing. So you will say that a tuple M1 to M theta is say, you are in the composable case when you don't admit the composition into 2 pieces, non-zero pieces, of course, with such that the square of the braiding between these 2 pieces is the identity. So this is kind of a natural extension of the definition I gave you before, but now for more than 2 summands. You don't have to think too much about this case. It's just a natural way of extending the definition of the composability. And then we need some way to put the structure of the modules that we will get in the classification into some efficient way, right? Like some efficient way to codify the information of the modules. And we are going to do this. What we are going to do is to put this information in Dinkin diagrams. So since we are going to consider Dinkin diagrams with some decoration, with some labelings, well, we call them skeletons, but they are essentially Dinkin diagrams with some decorations. Like, for example, this is what you see in type ADE. So this is essentially the classical Dinkin diagrams of type ADE, but with some variation, right? Because you see that in the vertex, you don't have only 1 point, you have 2 points. Why we have 2 points? Well, this is just a way of telling the reader that, this, say, this module, the module that you will have in type A will have this component, and all these components, but the dimension of each component, each MI, will be 2. These 2 dots are saying that the dimension of each component will be 2 dimensions. And you see that in type ADE, as somehow you should expect, this is kind of very nice, right? There are not so many decorations. It's pretty nice. If you go a bit outside classical ADE or like ADE type, then you get some diagrams which are similar to type type B, C, or F4, but with a bit more decoration, right? Why we didn't include like these diagrams in the case of 2 summands? Well, you could do that, but you have a lot of exceptions in that case, so it doesn't look good. What happens is that as long as the number of summands grows, then things tend to be like more nicer, more classical somehow. So with only 2 summands, it's kind of a mess because it's very exceptional. With 3 summands, looks a bit better, but then if you have a lot of summands, then you are kind of very close to have a very nice Dinkin classification. So the theorem that we proved with Heckenberger, again, around 10 years ago, is the following. So suppose that you have a tuple M1 to M theta that produces this kind of decomposable Dieter-Greenfeld module with the definition I gave you before, then you will have a finite dimensional Nichols algebra there if and only if the Dinkin diagram that you can attach to your module M or your tuple M is of finite type. Okay. So again, this is just the starting point, because with this information you can get whatever you want, right? You can get, for example, a very precise description of the modules involved. Like, and also, of course, the dimension of the Nichols algebra, right? Like, for example, this is the table shows the dimensions that you get in the case of Dinkin type ADE. Like in this very nice classical case, well, these are the dimensions you get, okay? Very good. Of course, if you want, you could get an explicit description of the group, but this is not so important, right? Because it's less interesting than in the case of two summands, because 2 summands were like too exceptional. This is less exceptional somehow. Now, let's go to the open case, the indecomposable case. What is this? Well, the point here is that we know only a very small list of finite dimensional examples, right? this is the whole point here. This is the full list of examples we know. So here I'm just listing the dimension of V, and I'm listing the dimension of the Nichols algebra of V. But of course, I could tell you which is the Jeter-Drinfeld module, right? Like, or over which group this you can realize. For example, the last two are realized over the symmetric group S5. All the others, well, smaller groups, okay? So a natural question is if this list, which is the list of the finite dimensional Nichols algebras over in the composable modules over the complex numbers that we know, is the full list or not? We don't know. So yeah, this is the question, right? Can you find another one or what? And yeah, let me show you, before trying to answer at least partially this question, let me show you an example about a module, like, a Jeter-Drinfeld module that produces one of these finite dimensional Nichols algebras. So let's say that you fix n bigger or equal than 3, and then you take xn, the conjugacy class of the transpositions in the symmetric group Sn. Then you take Vn as the complex vector space with basis in this conjugacy class, more or less. And then the braiding is just conjugation with a minus, right? So the question is, okay, when the Nichols algebra of this guy is finite dimensional or infinite dimensional? And you see that this will be finite dimensional for n equals 3, 4, and 5. This is quite old. This is from the 90s. The first two cases were done independently by Fomin and Kirillov doing Schubert calculus, and by Milinsky and Schneider doing Hopf algebras. The last one, I don't know, maybe it was also known by Fomin and Kirillov. This I don't remember, but for sure it was computed by Andruskiewicz and Grania a long time ago. And Fomin and Kirillov that found these algebras made somehow these two conjectures that I would like to mention. The first one is from the n equals 6 on, these guys are always infinite dimensional. And also that these algebras are quadratic, meaning that they only have quadratic relations, right? So the relations that you have in higher degrees are, like silly consequences of the relations that you have in degree 2. These two conjectures are open, and this is kind of the problem that's still open in this area, I think. But it's kind of hard. So recently, in an attempt to answer the question about, do you have another example of a finite dimensional Nichols algebra or not, with Heckenberger and Meir, we proved the following theorem, that we don't have another example as long as the dimension of V is a prime number. So the theorem is like this. So you have a non-abelian group, G, and then you have an irreducible Jeter-Drinfeld module over G. But here our field is the complex number. So we assume that the dimension of B is a prime number. The support of B generates G. Again, this is the assumption to say that, okay, the G I have is the one that I need to realize my setting, my module. And the dimension of the Nichols algebra of B is finite. Then, well, the Nichols algebra that I can produce in this setting is one of the algebras that I know. So this is the list of algebras that will appear here, which were some algebras that I had in the previous table. Okay. And the methods that we use to prove this can be pushed forward to get a stronger result, which is the one I want to mention now. This is a recent result in collaboration with Nicolas Andruskiewicz and Istvan Heckenberger. The theorem says like this: suppose that G is a solvable group. We put non-cyclic because, if it is cyclic, it's abelian, and then we are inside this diagonal type case, which was solved. So suppose that is a non-cyclic solvable group, and you have a Jeter-Drinfeld module. Again, you take the same assumptions as before, right? That the support of B generates G, and the Nichols algebra is finite dimensional. Then your algebra is one of those that you had before, right? So this is the list of possible Nichols algebras that you can get. But remember that you have a finite Nichols algebra over S5, right? So this, we don't know what happens over the non-solvable case. We have at least 2 examples that were listed before. We don't know if there are other examples over non-solvable groups. Over solvable groups, we are done, right? And yeah, so this has a very nice application to the theory of algebras, because as an application, you can get some sort of Fay-Thompson theorem for finite dimensional pointed Hopf algebras. So essentially a theorem of like this, right? If you have a pointed Hopf algebra of odd dimension, then you can have a very precise description of this Hopf algebra. Okay? And well, okay, what about the complement of this solvable case, right? So there is a conjecture that you know, that this has been there for a long time, that says that if you have a finite simple group and you have a non-zero yet a Drinfeld module over G, then the Nichols algebra will be infinite dimensional. This conjecture, well, there is some evidence supporting the conjecture, right? Like, for example, I don't know, maybe 20 years ago or even more. This is kind of sad to try to count how many years. But with Andruszkiewicz, Fantino, and Grania, we proved that the conjecture is true for all alternating simple groups, and also for 23 of the 26 sporadic simple groups. There are 3 open cases there, which are the Fisher 22, the baby monster, and the monster. I think that with the tools that we have now for this, that we used for this solvable case, one can get rid of these 3 cases. And for the, you know, for the majority of simple groups, those groups of Lie type, there are a lot of results that have been obtained by in several different papers, but by Andruszkiewicz, Carnovale, Constantini, and Gaston Garcia. But still, we are a bit far to be able to, you know, to prove or to disprove the conjecture, right? I think that's it. Thank you.